My name is Fabian Schumann. I'm from the chair of Automotive Technology. And yeah, I have the honor to present to you rescuePY today. I want to start my talk with actually having a look backwards. During the last 10 years, we saw an increase on the average travel time of emergency medical service of 1 minute 31 seconds on average for every city in Bavaria. Due to the mobility transition to a more sustainable mobility, we see quite a lot of changes. For example, the reduction of speed limit, or also the changes inside our street space. So now the question for operators of emergency services arises: how do actually those mobility innovations influence our emergency medical service? For sure, seeing this little animation, actually the travel time is the value to go. Nevertheless, in the current state of the art, considering what-if scenarios is only possible in a limited way. And due to the, let's say, increasingly and rapid changes in our mobility system, a comprehensive and interlinked analysis will be necessary in future. So, welcome to my today's talk about rescuePY, as already introduced, a tool for the simulation-based emergency service impact assessment. First of all, let's go one step back. What actually happens when you detect an emergency? So when you detect an emergency, you, in normal situations, call the 112, and you will talk to a disponent and, let's say, tell him what happened, what forces are needed. The disponent actually assigns some forces to the mission. The forces will get equipped at the station, and afterwards they are deployed to the mission. So they are taking the fire car or fire truck and go to the scene. At the scene, they will treat the emergency in case it's locally limited. In case not, we potentially need to evacuate the scenario. Once the treatment is done, the forces will go back to the station. Now, having a look at this, I would say, simplified rescue chain, we can analyze three main spots where mobility innovations can influence it. First of all, we have the strategic part, the strategic planning. Questions which arise here are where to position our stations in future, or even how to equip those stations. We have the operative planning part, where questions arise like how do traffic lights, for example, influence our emergency vehicles, or how do structural changes to our street network influence it. Last but not least, we also have the question of evacuation planning, arising the questions of how do evacuation times or rate of evacuation change. Having a look at all those three categories, we can find already in the state of the art quite good methods. For example, especially in the operative planning, the model developed here at the DLR. Also, we can find some regulations coming from different, for example, fire departments as listed here, which already give you an advice how to handle the situation. Nevertheless, you can detect a lack of a tool-based and holistic consideration of changes in mobility, for example, infrastructure and demand, and their impact on the rescue services. This is actually the gap rescuePY wants to address. By applying three different kinds of models combined in one platform, namely we are applying a mesoscopic simulation for calculating the system behavior of the rescue system. We are applying and have further developed an interaction simulation, so namely a microscopic sumo simulation for analyzing detailed travel times. And last but not least, we have a microscopic and multimodal evacuation simulation inside our platform, which allows to analyze evacuation times. All those three models are combined inside our rescuePY. rescuePY is actually a plugin for sumoPY or hybridPY. It uses the mesoscopic as well as the microscopic sumo simulation. It's available in Python free, and it has customizable data input, which allows us to easily import our own data in case we are an operator of such an emergency service. Now let's have a look at the first module of rescuePY, the strategic planning. So the question we actually want to address is, does our system meet the requirements to a sufficient degree? We can actually easily simulate this by putting the rescue stations and the equipment along the transport infrastructure with some assumptions taken from literature into the simulation and see how our rescue system reacts to the demand, namely the fire alarms. The architecture of the module is, as already said, we simply can import on a CSV file basis the rescue stations as well as the rescue equipment, so we actually can simulate which vehicle is stationed at which station to which kind of alarm can it really respond. We can easily import the alarm data, which can be taken from the operation management system, so we have quite a flexible import which allows you easily to adjust this import to the data you have inside your system. Along the data we need actually the coordinates, we need the time, and we need the type of emergency, so we know which vehicle to send. And we simply can import the traffic network. For the strategic simulation we are using the mesoscopic sumo simulation due to the fact that it's more robust against system or traffic network failures. And along those definitions we also need to import the zone definitions, which are the basis for doing the planning of which vehicle should come to which emergency, and also the expected travel times on different links, which we, for example, can import using the operative planning. Once we have all data imported into our rescuePY framework, we can calculate the station order. I will later explain what this algorithm does using actually the hybridPY framework. And then we can put everything into our sumo simulation, implement it in Tracy, and once the simulation is done, we can easily do, for example, here a duplicity analysis. In here I've got one picture how actually our user interface looks like. So you can see the rescue system analysis is a plugin. On the left side you can see the data we simply can import. You can click on these objects, you can also edit them. And that's one of the main advantages of using this sumo-Py hybridPY framework. We, for example, also can visualize our data. For example, here we can easily visualize our fire stations. We could also easily integrate into the user interface other kinds of data. Now let's have a closer look at actually our implementation, which is in the back. First of all, calculating the station order. This is implemented inside our hybridPY framework, wherein we have for every zone we calculate the send read, and afterwards we do a routing to every fire station. Once we have the routing done, we can estimate the time of arrival, and then we can calculate an order based on the expected travel cost, which fire station should respond to an emergency first. This, for example, allows us that we can easily also change our network we have imported into the hybridPY framework, and we can, for example, adjust our alarming logic for real use cases. Second, how do we afterwards simulate everything? As already mentioned, we are using the mesoscopic sumo simulation. We are actually, once we receive a call, we simply dispatch a vehicle. Once we dispatch a vehicle, we insert an emergency vehicle into the simulation environment alongside and stop, which takes into account the duration of actually the treatment of the emergency. And once we are actually done with the treatment, we insert a normal truck backwards to our fire station, and we can go back. On the next slide, I've got one short example. As we already have heard yesterday, seeing is believing. We have made a little animation which allows you to see the fire stations you have imported. You can see also the alarms displayed by the green rectangles. The fire stations are the red polygons. And then you can see the system, how it responds to different emergency situations. So having now a look at the results of the strategic planning, we simply did a comparison for Munich. We got the real alarm data for 1 month in the year 2013, and we compared the travel times to the actually measured travel times. And the result is depicted in here. So what we actually can see is that for mainly off-peak times, our model already estimates, I would say, acceptable numbers. Nevertheless, you can also see inside our current state of the model that we need to take further constraints, for example, traffic and also other constraints into consideration. The strategic planning module, as said as an introduction, is based on average travel times. For the current system and current traffic situations, the easiest approach is simply to measure travel times and to bring it to simulation. Nevertheless, if we have a look onto future scenarios, we also need to have a simulation-based estimation because we do not have the possibility to measure. Therefore, our approach is that we do a micro-simulation of a certain sub-area, which we simply iterate over random seeds and afterwards get the average travel time. In here also we have a link again to our hybridPY framework because, for example, the traffic demand which we are using in our smaller sub-area we can derive using the hybridPY approach we have presented yesterday. Now, if we want to simulate a new mobility situation, using the current state-of-the-art implemented in Zoom, it probably would look like this. The non-emergency vehicle would align to the left because it tries to form a rescue lane, and the emergency vehicle will be behind. For simulating especially future scenarios, we have implemented and enhanced the logic. First of all, we have, let's say, made the blue light device of the emergency vehicle switchable due to the fact that we can simulate the fact that we respond and go back. We have adjusted the alignment of non-emergency vehicles depending on the number of lanes. We have implemented logic that the stuck emergency vehicles get teleported because we saw in the simulation it happens from time to time that when the emergency vehicle is overtaken, it gets stuck in the opposite traffic. And last but not least, we have implemented a logic that the non-emergency vehicles can use, for example, sidewalk or can use a bicycle lane to park on it to give the right of way to the emergency vehicle. And as well, the non-emergency vehicles can temporarily ignore traffic lights. The first two changes are made to the C++ code, and the other three are made as a crazy logic because this gives us the opportunity or possibility to easily adjust the values. And using those changes, actually, the situation looks like this. I've brought a small example. In here now you can see the emergency vehicle overtakes the other vehicle. The color of the non-emergency vehicle depends on the current state of detection it has compared to the emergency vehicle. And first, or now I want to, let's say, present a small plausibility check of the model. We have created a subsection, the Schellingstraße, wherein we put in the rush hour demand and wanted to see whether the current changes already did or give us a plausible result. First of all, you can see here on the left, our changes to the model actually worsened the travel time. What we could see inside the system, that in the current implementation of Sumo, the non-emergency vehicle, which could also be bicycles, align to the left and the emergency vehicle can overtake onto the right. By aligning the bicyclists to the right, the emergency vehicle in our current simulation with the current parameters does not overtake anymore. Having a look at the 200% demand, we see the expected result of our model. Last but not least, I want to briefly introduce also the current state of the evacuation module of our rescuePY implementation. As basis for this, we are using an activity-based travel demand, and we have introduced inside the hybridPY environment a logic to adjust the activity schedule based on an evacuation order. So whenever we get an evacuation order, for example, at 12 o'clock, we adjust the schedule that whenever the workplace is within our evacuation area, we insert an evacuation activity depending on our departure time model going to the shelter area. Whenever the workplace is within the evacuation area, but the home is not within, we make the persons go home. The current state of the emergency planning module allows us now to import a synthetic population, as we, for example, have with the demand model for our Munich scenario, allows us to import the facilities and also the traffic network and define inside our graphical user interface actually the evacuation zones based on the harm zone and the shelter zone. Afterwards, we can put everything into our SUMI simulation, which is also mainly a Tracy simulation based on an adjusted waiting for our routing, and we simply do rerouting during that time. And afterwards, we are providing an evacuation time analysis module. Now, to sum everything up, I've presented to you the three potential and three areas where mobility innovations can actually affect our rescue chain. I've presented to you our platform rescuePY, which allows you and allows operators of rescue infrastructure operators to do analysis how potential changes in mobility influence their system. And I've also shown you some first results using our method. Within the strategic planning, we are integrating further EMS services and also further logics. For example, we have quite a high number of voluntary fire departments which also need to be taken into account. We have also the emergency medical services which need to be taken into account. Second, we do a parameterization of the model with the real-world data measured in Munich. For the operative planning, we are planning to parameterize our model based on survey and videos. We are currently gathering the data to do this parameterization, and we are also then validating the model with the parameters we got to the real-world data. And last but not least, for the evacuation planning, we are planning to implement our tool and our method I've presented today to a real-world use case and real-world scenario and adaptive. So thank you very much for listening, and now I'm ready for your questions.